Hi, I'm Tim with Legacy EV, and today we're going to be diving into the Emus G1 centralized BMS system. The system is modular and flexible and great for a wide variety of both stationary storage and e-mobility applications. In this video, we're going to go over some of the hardware that you might encounter in one of these systems. We're going to go through how we've connected it on one of our benches, and then we'll also take you inside the GUI or graphical user interface to show you some of the different settings and parameterization that you can do with one of these systems. Finally, we'll walk through a simulated charge and discharge cycle so you can see how their unique algorithms make your batteries last longer. Before we dive into the hardware we have out in front of this table, let's give a little bit of context and background about Emus and the company they are today. They were originally started in 2010 after the founder and still now CEO took on his own EV conversion project. He quickly realized there was not a BMS system that fit his needs. Now, with over a decade of experience in the custom BMS market, they're well equipped to offer a wide variety of solutions depending on your needs. It's currently headquartered in Lithuania and had established their US branch in 2021. Today, Emus BMS solutions are used worldwide in e-mobility applications, stationary storage applications, robotics, maritime systems, and even other specialized applications. What makes the Emus BMS product line unique is how configurable and scalable it is. For example, they have solutions for a 6-cell battery pack that you might see in a scooter, all the way up to 6 megawatt-hour stationary storage systems. But what's cool is it's all using the same type of hardware and systems, so you can stack, build, and add things as is needed in your particular application. Beyond the hardware and software, Emus BMS also offers class-leading support and accessibility with next-day support via email or call from any of their technical engineers, a free-to-use and download configuration software, as well as 2 to 4 day shipping within the United States for products in stock. Now that we have a little bit of context about who Emus BMS is and what they bring to the marketplace, let's dive into some of the components that make up their configurable systems. Today we're going to be demoing the Emus G1 centralized control system. It uses centralized topology in which we have one controller and then several CCGMs or cell control group modules that are all connected via CAN bus back to this control unit. Additionally, we'll also be going over some different current sensor options as well as a lot of the pre-made harnesses that makes installing this system really easy. First, let's take a close look at the G1 master controller. This unit manages all safety logic, all control logic, CAN communications, and inputs and outputs with other systems. It's configurable in that in a lot of different applications or large applications, you can connect up to 18 of these modules together. However, in most EV systems and ESS systems or stationary storage, only one of these is needed because, as we'll get into later, they are capable of managing 512 cells by themselves without the need for extra controllers in that network. The G1 master controller has several different options for connectivity, including a USB interface, CAN bus, and serial. So whether you're communicating to a laptop, a PLC, or another VCU in an EV application, you're good to go. Another point worth mentioning is the I/O flexibility. So rather than there are some fixed inputs and outputs, and there are some flexible or configurable inputs and outputs. We'll get into that a little bit later when we dive into the GUI and how you would configure those. But for now, just know that flexibility gives us a lot of different options when it comes to vehicle or system control. Next up, let's take a closer look at the centralized cell group module, or CCGM. These can monitor anywhere between 6 and 16 cells with passive balancing capabilities, configurable up to 300 milliamps per cell. Beyond that, we also have 5 thermistor connections for monitoring temperature within your battery pack. It also features 2 CAN ports so that we can daisy chain multiple CCGMs as well as other hardware on our CAN network. One other thing to mention is that within these units, the high voltage sensing circuits and then the control and communication circuits are galvanically isolated from each other, which means long-term, your battery pack system is safer and more reliable. As we talked about before, this system overall is very configurable. For that reason, one control unit can monitor and communicate with up to 32 CCGMs, with each of these CCGMs capable of monitoring up to 16 cells. That means in total, we're looking at 512 cells for one control unit. Emus Bms provides 3 different current sensor options for your G1 centralized system. The first option is a busbar dual range sensor. It uses a Hall effect design and is designed to mount in line between cells and provides galvanic isolation and bidirectional accuracy. The next is a clamp-on current meter or sensor that goes around a cable. And then lastly, we have the CAN current sensor, which communicates all of its values over a CAN network, as opposed to the first 2 options, which are using analog signals to communicate back to the control unit. So depending on your particular application and design considerations and constraints, they've got a current sensor that is ready to rock and work for you. Let's dive into a couple different accessories that you might get with your BMS system. The first are these CAN hubs. So when we're adding multiple things to a CAN network, we're no longer having to splice into a CAN network. It's just plug and play with the included harnesses to plug into these devices and expand your network as you need. You'll need CAN termination on your CAN network. That is also made simple by these CAN termination resistors, which you'll end up plugging in at both ends of your network. I'll show you this all set up in just a little bit, so stay with me. Beyond these CAN devices, they offer a wide variety of pre-terminated harnesses as well. This, for example, is the power and USB connection specifically for the EMS control unit to get you up and running and parameterizing your system quicker. They also have pre-terminated CAN harnesses in multiple lengths, harnesses specifically for the current sensors, and so on and so forth. Here we'll also look at these pre-terminated cell harnesses and ones with equipped thermistors. In our application, we've made some small modifications so they can plug into our training battery boxes, which we use in our EV curriculum here at Legacy EV. Beyond what's here on this bench and a part of this demo, Emus offers a lot of other options for your application. These might include thermistor expansion modules, modules for cellular connectivity, remote connectivity, or even displays. All of those components are designed to natively integrate with the G1 control unit. Now that we've gone over what all the components do individually, let's get this system set up to monitor and control our battery system. So the first thing we're gonna go ahead and do is we're gonna take this control unit. Emus provides this optional harness that will allow us to easily connect to our laptop through our USB interface, as well as provides initial points for both our 12-volt power and ground and our CAN high and CAN low signals, which will interface with the rest of the system. So we'll take this, we'll go ahead and plug it in. There. In this particular application, we're gonna go ahead and use one of these 3-way CAN hubs right from the jump. Now, we'll take this CAN hub and connect it to our CCGM here through the CAN port. Remember that these CCGMs are daisy chainable, so we'll just go ahead now and connect it to the next one down the line. In this particular case, we've got 2 battery boxes, both with 15 cells. If you recall, both of these can monitor up to 16 cells per CCGM, so we'll just be using 2, 1 for each box. So we'll go ahead and daisy chain those together here as well. Another thing to keep in mind is that through this CAN network, we have our CAN high and CAN low signals, but also our ground and 12-volt signals. All these CAN ports are both inputs and outputs for those for our 12-volt power, and so we can connect anywhere along this line to our 12-volt power supply, whether that be a 12-volt DC battery in a vehicle application or a 12-volt panel-mounted supply in a stationary storage. With that in mind, we'll click into this next CAN port, and just so we can go up and leave a connection both for our termination resistor here, as well as our harness for our 12-volt power supply here. And then the last thing we're going to do with this CAN network is go ahead and put our termination resistor on this hub as well. There's a couple other things we might also want to connect at this point. The first is going to be, we're going to want this USB interface. So we'll connect that here. This will plug into our PC to access the control software. And then we're also going to use one of these current sensors, recalling that we have both analog current sensors as well as the CAN bus ones. In this case, for our demo, we're going to use one of the analog current sensors. In this case, the loop Hall effect sensor. And conveniently, we have a harness to connect that as well. So we'll have here on the control unit, we have an additional port to plug in there, and then into our loop sensor. Voila. This will go around our primary battery cables when we get into the demo. Next, the whole point of this is to be able to monitor our batteries. So what we've done is we've taken their pigtail harnesses. We have two that haven't been modified for our cell taps, and then thermistors as well. And we've modified them to adapt to our mil-spec connector, these mil-spec connectors, which will plug directly into our training battery boxes that we use as part of our training. So with that in mind, we can go ahead and we have here on these bad boys, here on the CCGM, we have a connector for the cell taps and another for the temperature sensors. We'll do the same here. Cell tap connections. These will be monitoring voltage and temperature sensors. So now, with the exception of being connected to the battery packs themselves through these mil-spec connectors and a 12-volt power supply, you can kind of see the whole system architecture here laid out on the bench. Now that we got the Emus architecture laid out here, we're going to go ahead and connect these cell taps and these thermistors to our battery boxes. Like I said earlier, we use these for our training. That's why they have the clear top. It makes it easy to see inside and see the cell tap connections, the bus bar connections, and the series parallel connections. Now that we got everything set up and parameterized, we're going to walk through the graphic user interface or the control panel for the Emus Bms to show you some of the options as far as configurability and data representation. So yeah, let's dive into it. So when you first log into the software here, we're going to be looking at the status page. This is just giving us an overview of a bunch of different things, how long the BMS has been up, measurement period, any errors or protections, battery pack specifics, if we had a CAN charger or inverter enabled, what those would be, charging process. So just kind of at a glance, what are the inputs and outputs, what's the battery pack looking like, that sort of stuff. Now we can go ahead and dig into cells here, where we'll see kind of our min and max cell voltage, the average, our total battery pack voltage. You can see here the graphs, and then if we want to, we can export these cell parameters as well. Similar here for temperature, and then also balancing currents. So what makes the Emus Bms balancing a little bit different than others is a lot of times as you charge up, some cells might get a little bit out of balance. And so in that case, most BMSs will go ahead and pause charging to allow them to get back out of balance or to get back to balance. But what's cool about this one is per cell, we can draw 300 milliamps from any given cell. So rather than pausing the charging process, we're going to just take the cells that are above a set voltage and actively bring those down. So we're not stopping the charging process. We're just on a cell-by-cell basis able to pull a little bit of current out there and get them all in balance again, which will long-term improve your battery health. It's a much better way and quicker way to keep a multi-cell lithium-ion or lithium phosphate battery pack in check. So right now we're only charging with a couple amps just because it's a test bench system. So you don't see much here in the context of any sort of balancing currents. And the other reason for that too is because it's pretty much a brand new battery pack. So that would be why. But yeah, you can see the kind of the cell stuff there. Then we can go ahead and look at some of the sensors. So in this case, we're using an analog current sensor down there to measure current. Again, just 1.4 amps, not much at all, just because it's a lab setup here. But in an EV, you might see, if you're using DC fast charging, for example, you might see hundreds of amps. If you're using like level 2, you might see, 40 amps or so. Just kind of depends on the system. So next we're going to move over to state of charge, state of health. State of health, we're just calculating how healthy is the battery pack overall. Over time, as you charge and discharge the battery pack, you'd lose capacity. And then state of charge is just from 0 to 100%, how full is the battery. Here we're gonna see 100% for both of those, and that's just because it's just a demo. We haven't had time to have this BMS run on this system in operation and calculate both state of charge and state of health. And lastly, we can go and check on what CAN devices, the status of the CAN devices. We only have 2 on this network right now. That is the both modules, which we talked about earlier. So now digging into some statistics. These are just collection of different statistics, the last events, can be useful in troubleshooting. And then similar with events, okay, the BMS was started, charger connected, disconnected. So key events are noted there in that panel. Now we'll dig in a little bit into the config and just kind of give you an overview of how flexible the system can be. So the first is you can set some security and some configuration stuff here, some resets, just some general management. Then we go into general, so this is selecting what kind of current sensor we might have installed, the different kinds of battery pack specs here. Then CAN, we can adjust different CAN speeds for different devices. If you're using really large systems, you'd want to use a CAN filter. When you have a lot of nodes on a network, not the case here, so nothing changes. Another important tab in the Emus BMS is the charging parameters tab, now shown here. This defines how the charging logic within the Emus BMS operates. It's a really effective tool to make sure that your charging protocol is designed for your specific system application and requirement. For example, we have 3 kind of different stages of charging. The main charging stage is entered when the maximum cell voltage is below the fully charged voltage parameter value and no other stage entry conditions are met. This indicates that no special precautions are required for safe charging, and therefore, in that stage, the battery can be charged with the highest possible current. Actual charging current depends on the control's unit configuration parameters, as well as the physical limitations of whatever charging device you're using in your system. Some key parameters in this tab include the fully charged voltage. This is going to be set based on your battery's particular chemistry. 4.2 volts, for example, is common in batteries with NMC chemistry. The allowed disbalance is how far all your individual cells can be away from each other before we're going to enter a balancing stage and activate the balancing algorithm. The early balancing threshold shown here is the cell voltage level where the balancing algorithm activates. Pre-charge threshold is the voltage limit used by the charging algorithm to decide when to begin charging at a lower current. Now up here in the right-hand corner, we have the fast and slow charge current, which is the maximum charging current requested from the charger of the inverter during the charging process. We also have a pre-charge current, which is the maximum charging current requested during a slow pre-charge phase. And lastly, the charge finish current, which is the current at which the charging algorithm determines that the battery is now completely charged. In some applications, you might need additional charging parameters. This is another area where Emus delivers significant benefits, especially when working with inverters, like in an e-mobility application. For example, under configuration, charging, and charging tuning parameters, you'll find that these settings define the charging increment and decrement step sizes at different battery cell voltage levels. Additionally, the safety margin current parameter limits the requested charging current above the actual charging current. Together, these parameters ensure a stable and controlled battery charging current within the Emus G1 battery management system. Over to the next one. So this is where we can tune in how SOC and SOH, state of health, state of charge, are calculated. What's pretty cool about this BMS system is a lot of BMS systems use what's called Coulomb counting, so measuring current in and out to get an understanding of what capacity a battery pack has, which is a fine model. But in this case, we're using the Kalman estimator, which is a little bit more accurate. It's treating every battery cell as its own circuit. And so here in the cell model reference settings section, we can set some of these different cell specific values as well as capacity. Clicking on this button here will open up the actual charge discharge curve. So because of that, we can get a really accurate understanding of capacity left even as the battery ages, because the Kalman estimator is taking in all these things into account. Similar state of health parameters, how many charges before you start to lose capacity in that sense. This one, in some cases, you might not want a user to see the full state of charge. By limiting those at 10 or 90% true, you can preserve the life of a battery pack. So just a ton of options here about how these things are calculated and how they're represented to a user via CAN or a different display. Going into some of these other sections, protections, warnings, reductions, you'll see a lot of similar stuff on these couple. And really just giving us ways to either send these messages out on a CAN message, either as warnings or limiting or blocking faults. So this includes when they might activate at, when they could deactivate it, how long does it take to activate. So you just have a ton of control over protections and faults here, as well as warning messages. And then not last, but up next we're going to get into the controls panel. So there's a couple other things we can control here. We'll get into some of the configurable I/O in just a second, but you can see we can directly control battery contactors, climate control for our batteries, the DC-DC converter, heater and fan, so on and so forth. So useful for some of these I/O pins that are here. So we have some set IOs, and then we also have some configurable. So if you could just kind of take a scan through here, we can have one for ignition key input, charger enable output, speed sensor input. So there's a lot of ways that we can go ahead and have inputs and outputs for different applications. So it makes it really flexible. And because we can either use I/O pins, we can control it directly with this device, or using a CAN message, maybe a VCU could be directly controlling some of these outputs. Here we're just going to kind of see how many CCGMs or these cell satellite modules we got on the network. We just have the 2 with the serial number, nothing crazy there. Similar with the CAN group module here. This sort of window makes it really easy to have multiple parallel strings in any one battery system, and then anything in series goes here. So you can kind of see our 30 cells that are here reflected in that. Relatively straightforward to get all that set up. And then that's mostly it for a lot of these different settings. If we go into the update, we can discover different devices on the network and update them with different firmwares as required, and similar with the control unit as well. So depending on the charger or some other things you might want to do, you can dig into and get the correct firmware for whatever you hope to have or whatever functionality you want to have on that network. And then really lastly here we got where you'd have other external components. Nothing set up here, so it doesn't make a ton of sense for this demo. And that's just a quick rundown through the Emus control panel. Everything's pretty straightforward within here, I think, and it really makes it easy to both understand and then understand your data, and then also manipulate how your BMS behaves depending on what you're trying to do in any given application. And then also, you know, like a lot of software hovering over certain things will give you, you know, some kind of specifications to help you along the way. That's it for today. Thanks for joining us as we dug into this Emus Bms system and all the reasons why it's flexible and configurable. In my mind, there's several things that make this BMS system a unique value proposition. First, of how its plug-and-play simplicity is a great benefit. Secondly, the customizable control panel and the ease of use there makes it easy to understand what the settings you're manipulating with the data means. It also has robust technical specs, ability to interface with other VCUs, PCs, PLCs, and other components through analog means. And lastly, it's accessible and supported. You get next day access to Emus engineers, and in most cases 2 to 4 days before these parts are at your door. So if you want to learn more, visit emusbms.com or legacyev.com to understand how this solution can fit into your projects. Also, feel free to download the free software and start playing around with some configuration. And if you need system design support, Legacy EV is here to help. Thanks for tuning in, and we'll catch you next time.